Welcome to the third lecture. So, I would like to start by reviewing a little bit what we did yesterday, because I feel that it was a bit overwhelming, especially to the very end. So let me flesh out the punchline of yesterday's results. We did several things. Let me start here. So yesterday thanks. Yesterday we did several things. First of all, we defined what are conformal transformation. And we obtain that they are generated by, it's a group generated by translations, Lorentz transformation, dilatations, and then there are a set of new transformations which are called special conformal transformations that you can, in a sense, think as taking the inversion transformation, composing with translation and invert again. I stress that the inversion is not, strictly speaking, is not part of the group because it's not connected to the identity. It's a discrete transformation. But nevertheless, you can have this intuition. And we obtain the algebra, and we also studied irreducible representations of the conformal symmetry, and we discovered that they are made out. You can think of an irreducible representation as an infinite tower with a ground state, which is the primary, and all the other states are called descendants. And you can move up and down in the irreducible representation using the generators P, N, and K. And the primary has the property that is annihilated by the special conformal transformation. And also we obtain the transformation properties of fields. So we obtain that a field which belongs to a primary field that belongs to some irreducible representation of the Lorentz group with index I, collectively called I, under a conformal transformation, transforms like a prefactor, omega to the power delta. This omega is an x-dependent prefactor, which changes depending on which transformation you are considering. Then there is a rotation, an orthogonal transformation in the appropriate representation of the Lorentz group, which construct the indices. Okay, and using this information, we obtain the general form of correlation functions, which are the main object of interest in our in a conformal field theory. And in particular, we obtain the following results. 2-point functions, operators can be brought in a form that are diagonal. So in particular, if you have scalar operators, I or j, this will be written at least in a unitary theory, divided by the norm of the difference of the coordinates to the power 2 delta, where delta is the dimension of O I, which has to be equal to the dimension of J. And similarly, we obtain a formula for operator with spin, and also in that case, we show that there is a uniquely fixed form for the 2-point function. So if you have an operator with spins, let's say traceless symmetric operators with L indices, new one, this can also be written in a form. Also, this one has to be diagonal, and its kinematic form is completely fixed, and there is the usual prefactor that takes into account scaling dimensions, x minus y to the power 2 delta, and then there is a tensor structure which is uniquely fixed by conformal symmetry, which has the form u I mu1 nu1 I mu L nu L plus symmetrization and minus traces. And this tensor here, I, is called the inversion tensor. Mu nu is basically the metric eta mu nu minus 2 as a function of x. And this is a function of x minus y. Eta mu nu 2x mu x nu divided by x squared. Okay, so this is a very powerful statement. We are saying that correlation functions are completely fixed. Two-point functions are completely fixed by the conformal symmetry. And the prefactor, so in generically you can have a constant here, but can always be reabsorbed in the definition of the fields. So that's I will always use a normalization where the fields are defined through this with this normalization. And a third result that we obtain, which will be useful for us, is that three-point function can also be computed in, can also be fixed by conformal symmetry, and in particular, the three-point function of two scalars. Let's say O1, O2, x1, x2, and then a traceless symmetric operator, O3, mu1, mu L of x3. This is also fixed, and it has this form, the following form. There is a denominator which is x12 to some power alpha 1, which I will write in a second, x23 to power alpha 2, x13 to power alpha 3, and then there is a tensor structure that takes into account of the indices, and this is z1 to 3 mu1, z1 to 3 mu L minus traces to make it traceless. And this vector here is the only vector that is invariant under, that has the right properties are under conformal transformation, and is defined to be xik divided by xik right here it's modulus or not modulus. Yeah, I should have modulus. Minus xjk. And the power alpha 1, alpha 2, alpha 3 are of the form alpha 1 is delta 1 plus delta 2 minus delta 3 plus L. Alpha 2 is delta 2 plus delta 3 minus delta 1 plus L. And alpha 3 is delta 1 plus delta 3 minus delta 2 plus L. Okay. Okay. So this is again a result, but then in front of this in front of this tensor structure, which is uniquely fixed by conformal symmetry, there can be now a constant, which I will call C1 to L. And this constant cannot be reabsorbed in the redefinition of fields. So this constant will play a fundamental role in our discussion. And you will see, this is called OP coefficient, for a reason that you will see shortly. Okay. So again, also three-point functions are completely fixed up to a constant in by conformal symmetry. Yes. You have to make this object traceless. So if you contract any two indices, you must get 0. So basically, this is totally symmetric. Then you contract two indices, you must get 0. So you probably have something like z square eta mu1 mu2 plus other terms. You have to subtract these terms, okay? So that whatever trace you take, whatever indices you contract, you get 0. This is totally fixed. You can work out. Okay. So today we are moving to a different topic, which is the radial quantization. So there will be less computation and more concepts. So I really invite you to ask as many questions as you want. If something is not clear, just raise your hand and ask questions. So far, I've been using correlation function defined as insertion of fields inside some path integral, but I haven't actually defined what the path integral is or what is the quantization that I'm using. So the idea of today is to define this path integral properly, define in which direction we are quantizing, which direction we are evolving the theory, and using this approach, we can also identify what are the states, how they are related to, how they are related to the operators present in your conformal field theory. So let me give an introduction. Generically, when you quantize the theory, you have to decide, you have to assign a foliation of the space-time, and then basically you're defining a time direction under which you are evolving the theory. So normally, if you have RD, okay, so we always work in Euclidean today, and unless I explicitly say it, I will work in Euclidean space. And so, normally what we do, we define foliation. Well, first of all, we identify a direction which we call time. Okay, and then we foliate the space-time with space-like slices. Okay. And quantization means that if you have a state defined on some some space slice, then you want to evolve the state to a different slice. And to do that, you define a time evolution operator. And normally, the time evolution operator is the Hamiltonian H, which you can identify as the zero component of the translation operator. So this is very convenient in quantum field theory, but in conformal field theory it's not very convenient. And the reason is you would like to work with eigenstate of the evolution operator, so that if you start with an eigenstate if you start with a pure state, when you evolve it, you don't end up with a mixture of state. You want to remain on pure state if you want. But we have seen that in conformal field theory, for instance, a primary state or any state of this tower is not an eigenstate of translation, because if you act with translation or with P0 on any of the state, you end up with a different state. You move up in the tower. So this is not very convenient. It can be done, but it's not a very convenient choice. A better choice would be to use a direction of time, a direction of evolution, which preserve the state of your theory. And what is this operator? Well, the operator is, so a more convenient operator to use as evolution operator is the dilatation operator. If you act with the dilatation operator on any of the state of the irreducible representation, you don't mix it with other states, right? Because each of them has definite dimension. But D is the generator of dilatation, so it's not the generator of translation in time. So acting with the dilatation means that you are squeezing or enlarging some portion of the space-time. So using the dilatation operator as time evolution corresponds to use a different foliation of the space-time, which is not the standard one in terms of slices at fixed time. Using the dilatation as evolution operator corresponds to the foliation of space-time, which is basically made out of concentric spheres. So we're going to foliate our space-time using concentric spheres, and then use as evolution operator our dilatation operator. Okay. This is called radial quantization. So the idea is to start from states defined on spheres instead of defined on slices at equal time, and then use the dilatation operator to evolve states from one sphere to the next sphere. Okay, now that we have made this change of sort of perspective, let us see how actually operator of the theory indeed generate states on a sphere, so that you can associate to any operator, you can associate a state, and vice versa, given a state, you can represent this state, you can associate to this state an operator inserted somewhere in your space-time. Okay. Let me erase something. So I will use a path integral approach. So I need a few properties about path integral. So I would like to open a parenthesis on path integral. First of all, suppose you have, so what is a path integral? The path integral in quantum field theory is basically it measures the probability that you starting from a state, let's say, so you have a state defined on some slice of your foliation, you have a state, let's say psi. So you start with the state psi, and then you want to compute the probability. So this is defined some time initial. And you want to compute what is the probability to obtain a different state, let me call it phi, at some time t final. Here I'm using time as in a broad sense, okay? It can be the usual time evolution, it can be our radial direction, doesn't matter. And so in the path integral, this is given by an integral over all possible field configuration. Suppose your theory is defined in terms of some fundamental field O. There is an action which depends on the field O. And then you must specify some initial and final condition. In particular, you wanna impose that the operator at time initial is given by the field psi, and the operator at time final is given by the field phi. Okay, so this is the definition of a path integral. It measures the probability to pass from one state to another. Now, incidentally, you can use this object also to define states. Okay, so this is a probability, but if you basically strip off this part, you can define a state, an evolved state. And how is this defined? Well, the evolved state, so if you start from the state psi, and you evolve from time t initial to time t final with some evolution operator, u, this is nothing else that the same path integral where you don't fix the final condition. Basically, is a path integral with unfixed boundary condition. Sorry, here I said I was using Euclidean, so let's use Euclidean. So the initial stays there, but the final condition is left arbitrary. Okay, so this is a definition, if you want, of an evolved state starting from the state psi. You get the evolved state by simply integrating over field configuration without fixing the endpoint. And then by definition, if you project this state to the state psi, you get precisely the definition as before. And interestingly enough, you can also use this definition to define what is the vacuum state. And the reason is, if you send the initial time to minus infinity, because of this exponential damping, the contribution that matters is the contribution of the vacuum. So you can define the vacuum state, O, and there will be a definition of unnormalized vacuum state, because there is some prefactor which is the wave function of the vacuum, which doesn't really matter. You can define the vacuum as at time t final as the limit of t initial going to minus infinity of the above path integral. So you might ask how this object depends on the initial condition at time t initial, and if you define normalized state, this will not depend on it. So if you define a vacuum state normalized, meaning you divide by the norm, then this object does not depend on the initial condition phi. The way to see that this is true is simply, you can simply basically insert this. You can define as the evolution operator T final minus T initial acting on the vacuum time T initial, right? At time 0, sorry, at time minus infinity. And you can insert a complete set of energy states here, sum over n, En, En. And then you will see that the evolution operator acting to the eigenstate En simply gives you a term of the form e to the minus En. And so in this infinite sum, only the contribution of the ground state dominates. So that's why if you take this limit, everything else it's just suppressed. And what is left would be the projection of phi to the vacuum state, and that's the normalization factor, which you can simply divide off. Okay. So now using the path integral, you can define a vacuum state in this very nice form. Okay. So let's now go back to our case of interest, which is the radial quantization. So here the evolution operator is dilatation. So in this case we are evolving state defined on spheres from one sphere to a larger sphere, from one radius to the other. And using this definition of vacuum, we can define what is the vacuum state in our radial quantization. So suppose you have we have let's say a ball, so a sphere, and so this is the boundary of a ball. This is the ball, center at 0. Okay. So we can define the vacuum state, and this ball has a radius r. So using this definition, we can define the vacuum at some radius r simply by taking the path integral of our field weighted with the action of the conformal field theory, whatever it is. And then, as boundary condition, we leave all the fields unconstrained on the boundary of the ball. Okay, so we don't set any boundary condition on the ball. And then, if you look at this formula here, you have to take the limit of the evolution going to minus infinity. But in our case, the evolution going to minus infinity corresponds to sending the radius to 0. Okay, this is the only point, the minus infinity point, if you want. So in particular, generically, you could set any initial condition for your fields, since it won't matter once you define the normalized state, the normalized vacuum. Okay, so this is unnormalized. And in the normalized vacuum, this initial condition will not matter. So I will not even write it anymore. So the vacuum is, according to this discussion, the vacuum is simply the path integral inside a ball with no insertion of fields. Here, there's no insertion of the field in the path integral, and there is no boundary condition. Okay, so it's just a path integral with free boundary conditions inside the ball. This is the definition of the vacuum in radial quantization. And now you can ask, okay, what happens instead if I do something more interesting and I start inserting operator inside this path integral? So if you consider the path integral on some ball, okay, I'm not going to write these boundary conditions anymore. They're implicit. I'm just going to write the region of integration, which is some ball of radius r. And then I will insert in the path integral, let's say, an operator O in 0. Okay? And I would like to ask myself, what is this object? Well, this object, you can show very, very easily, and I will do it in a moment, that this object defines a state, which is a primary. So I will just denote like this, and is a primary, if O is a primary. Is a primary state. Define on the sphere, on the boundary of B, defined on dB. Okay, so by inserting an operator in 0, what we are doing, we are defining a primary state on the surface of the ball. The way to do that is, well, you have to act with a conserved charge, for instance, or with the generator of the conformal group on this state, on the state so defined, and show that it actually transforms in the right way. So this can also be written as operator inserted 0 acting on the vacuum. So this is what you get when you insert an operator at the center of the sphere. Now, if you instead insert an operator on a different location of the sphere, generically you don't expect to get a primary. And indeed you don't. So if you start with a path integral now, on some ball, and then you insert an operator O, x, where x here is inside the ball. Okay, so this is something like 0, and then you insert an operator here. Okay, so this object here, generically, I'll denote it like this. And this object here, you can see that by simply expanding the operator OX, this can be written as apx O of 0 to the minus px 0, but the vacuum is invariant, so this is just epx of 0 0. And so this is basically, if you expand in X, this is a superposition of 1 plus px plus dot 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 of 0. This is a superposition of the primary state and all the descendant, because P acting on a primary state gives you a descendant, P square acting on a primary state gives you second descendant, and so on and so forth. So this object here is infinite superposition of the primary state and the descendant. Okay. So by using this path integral representation, we managed to assign to any operator the corresponding state. So this is a part of the state operator correspondence. Given an operator, you can define a state on a sphere surrounding the operator. Of course, if you insert the operator outside, then you don't generate on the boundary of the sphere, you don't have anything, right? On the boundary of the sphere, you don't have any state defined besides the vacuum. So only when you insert an operator inside the sphere, on the boundary of the sphere, you create a state with the proper dimension and Lorentz transformation. If you insert the operator outside the sphere, then you don't do anything. So in some sense, not having an insertion is like inserting the identity. So the vacuum is associated to the identity. Primary state are associated to operators inserted at 0. Primary and descendants are associated to operators associated at some displaced operator inside the ball. Yes? No, you have to take the initial point going to minus infinity, which means sending the initial point to 0. So you have to integrate over the whole ball. So in this representation, if you want the analog of this, the probability, transition probability, would be integrating between two different finite radii. But if you send one of the radii to 0, meaning that you integrate over the whole region inside the sphere, that defines the vacuum if you don't insert anything. If you insert something, then you define a state.
It's analogous to the figure of time when you project conjugate states of energy. You could project
Right.
delta and you have the lowest delta.
Exactly, it's the same argument. Because sending the initial radius to 0 it means that you are, in a sense, performing a dilatation of from 0 to some finite value, which is an infinite amount of dilatation. So there is a projection there. Okay. This will become clear in a second when I will discuss the cylinder interpretation of the radial quantization. But now I would like to do the reverse logic. So now we have assigned states given the operators, and now I would like to do the reverse. I would like to, given a state, I would like to show that this defines an operator, so that they're really in one-to-one correspondence. And how we do that? So basically, an operator is defined through the matrix element with all the other states of the theory. So you just have to define matrix elements of operators starting from states. So now the reverse logic is the operator, state operator. This, in a sense, was operator state. Okay. So now, given the states, we would like to define operators starting from states, and the logic is very similar to the one that was before, except it goes the other way around. So suppose we want to define, we're going to give a meaning to a correlation function of some set of operators. Okay. We don't know what this means yet, because we don't have a definition of operators. We only have states. So let's say we wanna define what is the operator O1. Okay. Using translation, you can always translate the location of the operators, and for instance, we can set x1 equal to 0, just for convenience. So just put here 0. And now, what I can do, I can cut a hole around 0 of some radius. So this is my space-time, and I have operator O1 inserted here, and I have a bunch of other operators, O2, 3, On. Right? So I will define, I can cut a hole, so I can draw a sphere surrounding the origin, okay? And then I can replace the path integral that I had before. So this should be some path integral with insertion of O1 in 0, O2, x2, On, xn, e to the minus s. Okay, so I can replace the path integral inside this region. This is in some region R. Let's say, well, this is let's say it's on the whole space-time. So cutting this hole, I remove this region of integration, and I substitute this region of integration. So now it's going to be the integral on RD minus the ball. This is the ball. This is the boundary of the ball. So I perform a path integral over a smaller region, but now with some boundary condition that the operator O here on the boundary sorry, here this actually can go outside. Let me not write because it won't fit. So now we have the condition that on the boundary here, we have a boundary condition defined on the boundary of the sphere, and this boundary condition can be such that this, if you want the state, the value of the operator on the boundary has to reproduce some state. Okay, fixed. Okay, and so this is nothing else as performing basically. So what we are doing, this path integral here, where you remove the region, if you compare to the previous blackboard, is just evolving the boundary condition to the outside. So this is nothing else than a probability to start from some state O, 1, which is the one defined here on the sphere, contracted with the other operators, with some other state. Okay. So this we know is the state, is a state. So using this trick, cutting a hole and define the path integral as a matrix element between the state and the rest, we can give a meaning of correlation function. And you can iterate this for any operators. You can cut holes around any other operator. Okay, and then defining the path integral as an integration over the region, the cutted region, where you assign boundary condition inside, at any boundary of any ball, you basically can give a meaning to the whole correlation function in terms of states, because on each boundary you have a state defined. Yes?
Could you please explain again the equality between that path integral and the one on the right?
This.
Yeah.
So here, this is a path integral over the whole region with some insertion. Okay. Here instead, I'm basically removing this part. But when I remove this part, I have to assign boundary condition, because it's basically the reverse logic of before, right? An operator, if you want, the whole idea is to show that the boundary condition on the sphere can reproduce the operator on the inside, can mimic the operator, the presence of the operator on the inside. And as we have seen before, an operator on the inside produces a state on the sphere. So you can simply remove it and attach to it a boundary condition instead. Okay, and that would mimic the presence of this operator inside, which you're not probing because you have removed the region. Okay. So from one side we have defined operator and state. On the other side we have defined state with starting from operators, and so we literally have a correspondence. The correspondence in radial quantization is that an operator at a given location defines a state on the boundary of a ball that surrounds it. Okay. Good. Okay. So let's move to So let me give you a different interpretation of this radial quantization, because working with spheres is somewhat complicated. So it's better to work with surfaces that do not expand or contract. So in order to do that, let me make a change of variables. So the first, so in radial quantization, we are, as I said, we are foliating in terms of spheres. So a given vector, a given point inside R to the D can be written as, you can parameterize with the radius R, which is positive, and then some vector n on the sphere. R is in R plus, and n is a vector in SD minus 1. Okay. And now let me make a change of variables. I will define tau, which is the log of R. And so now, when you make a dilatation, you're sending R to lambda R. Yep. And this corresponds to tau plus log lambda. Okay, so this is a trivial thing, but it looks like that in this new variable, the dilatation looks remarkably similar to a time translation. So we would like to interpret tau as sort of time under which we are evolving. And there is a deeper meaning to this change of variables, which is the following. So let me make the following observation. If you write the metric in our in our radial coordinates, this is simply dr square plus r square d omega d minus 1. This is the metric on the sphere, dimension d minus 1. Okay, this is the usual radial, is the usual flat metric in radial coordinates. Now, when we change variables, this simply becomes e to the 2 tau d tau square plus d omega 1, which is the metric. So our original metric is conformally equivalent up to our scaling to the metric on a cylinder. Okay, cylinder is R times as d minus 1. So what this mapping does basically is visualizing our concentric spheres not as concentric spheres, but as slices of a cylinder. Right, so we started from concentric spheres, and then with this tau equal log of r, we're going to a different representation of space-time in terms of a cylinder, where each slice, so the vertical direction is it's tau now, okay, and it goes from minus infinity to infinity because r went from 0 to infinity, and then each slice at constant tau, let's say tau equals 0, for instance, or tau equal minus infinity, each slice is a sphere. Okay, And moving from one sphere to the other corresponds to moving in the vertical direction in the cylinder. And so this is very, very nice because it allows us to go back, in a sense, to a more intuitive picture of quantum field theory, where you have a time direction which goes from minus infinity to infinity, and then states that here were defined on spheres. Now they're also defined on spheres. But now time evolution moves you along the cylinder. So this looks literally like a usual quantum field theory, except that now the space, not the time space, not the space time, but the space itself is compact. It's a sphere of unit radius. And studying a conformal field theory is equivalent, as I will show in a second, to study a quantum field theory on a cylinder, where slices at constant time are spheres, and then you evolve spheres in time. And so our time evolution here was, if you want, the time evolution here was a dilatation operator. Here you can think of the time evolution as literally the Hamiltonian of the system. It's because it's evolving in this time direction. Okay, I think I'll take a break, 10 minutes break, and if there are questions. Okay, so we were discussing this cylinder interpretation. So with this interpretation, our conformal field theory basically is nothing a usual quantum field theory defined on this funny space. So far this seems like just a change of variables, but there's a deeper meaning that you can associate to it. And the reason is a consequence of Weyl invariance, if you want. If you remember yesterday, we said that in a conformal field theory, the trace of the energy momentum tensor has to vanish, and this implies invariance under infinitesimal Weyl transformation. So assuming that there are no anomalies, okay, infinitesimal Weyl transformation can be extended to finite Weyl transformation. If there are anomalies, you can even show that they don't really matter in the argument that I'm going to give. They will always cancel out. So because of Weyl invariance, there is a nice property that all correlation functions obey, which is the following. So if you have a correlation function, consequence, if you have a correlation function O1 x1 O(n) xn defined on some space with a metric G mu, this you can perform a Weyl transformation, and you can relate this correlation function to the correlation function on a rescale metric. O1 x1, On xn, with a different, on the space-time with a different matrix. Let me call it omega square g mu nu. But you have to pay a price to do that. You have to multiply by some rescaling factor, which is basically the product, I going from 1 to n, omega of xi to the power delta I. Okay, so there's this very nice relation between correlation function computed on one metric and correlation function computed on the rescale matrix times this rescale prefactor, and you can prove so the condition for this to be true is literally that T mu mu is equal to 0. And so now we are really in this condition, in this situation, because our original metric G mu nu was is the flat metric, but you can write this flat metric as a prefactor, so ds square flat. You can write as a prefactor e to the 2 tau ds square of the cylinder. And so we can compute correlation function on the flat space as correlation function on the cylinder, and vice versa. Okay, so sorry, the other way around. This is the flat space in our case. I wanna use this relation the other way around. So this would be our flat space, yes, and this will be the cylinder. So this relation tells you that correlation function on flat space define correlation function on the cylinder, and vice versa. They're related. So we can really use this cylinder picture to compute stuff. So, for instance, let me give you an example of a computation. And the cylinder picture is very nice because it's more familiar to us. It looks like a quantum field theory with a slightly different space. It's the spheres instead of, it's a compact space instead of infinite planes. And also the symmetries of the cylinder are very, very simple. There are rotations on the spheres and then time translation. So it's not very complicated. So to take this analogy seriously, let me define a quantity here. So given an operator in flat space, okay, define at tau n, I can associate to it an operator O cylinder tau n, which is defined to be simply e to the delta O tau O flat. Okay. If you have indices, the same relation goes true. Okay. And so the nice thing is that if I compute correlation function of this quantity here on my original spacetime, they correspond to computing correlation function on the cylinder of the same operator. So suppose I want to compute, sorry, and vice versa. Okay, if I want to compute, if I have my theory on the cylinder, consider a scalar on the cylinder. Phi. Okay. And I want to compute phi of hello? Okay. Phi of tau 1 and 1, phi of tau 2 and 2 on the cylinder. Okay. This thanks to this relation, this is equivalent to compute the correlation function on the flat space, but of the cylinder operator. So phi cylinder of tau and phi cylinder of tau 2 and 2, where phi cylinder is there is a scaled version of a usual operator that you would write. Phi cylinder is e to the delta phi tau 1 phi flat. And we know already how correlation function of phi flat look like. We obtained yesterday. So you just rescale them and you get correlation function of phi cylinder, and this should correspond to computing correlation function directly on the cylinder. Let's make an example. So in order to compute this quantity here, I can take simply my original, so that's phi cylinder is going to be something like e to the delta phi tau 1 e to the delta phi tau 2, and then the usual flat, the usual 2-point function, which is nothing else as 1 over in Cartesian coordinate. This would be x minus y, sorry, x1 minus x2 to the power 2 delta, okay, which I can rewrite as translating Cartesian coordinate to polar coordinate. This is simply, and this, remind you, this is just r1 to the delta phi, and similarly this is r2 to the delta phi. So this just becomes r1 over r2 to the power delta phi divided by modulus of 1 minus 2 r1 over r2 and 1 dot n2 plus r1 square over r2 square and everything to the power delta phi. Okay, and if you now rewrite this in terms of tau, this is simply e to the delta tau 1 2 delta phi divided by 1 minus 2 e to the tau 1, 2, and 1 dot n2, plus e to the 2 dot tau 1, 2. Whereas the usual tau 1, 2 is tau 1 minus tau 2. So interestingly enough, the result looks something that we should have expected, is invariant under rotation on the sphere. It only depends on the scalar product of the two vectors. And it's also invariant under translation. It only depends on the difference of the time coordinate. So there's a function of tau 1, 2 and the scalar product, which is something you should have expected, you should have guessed, because this is a result of a two-point function on quantum field on a quantum field theory which is invariant under rotation and time translation. Very nice. And also, we can do another exercise. You can expand you can write this object as, perhaps I can just write here. You can do a sort of Le-Manchal decomposition of the two-point function. And so phi cylinder, you can expand this object and write it as a sum over n some coefficient Cn e to the minus delta plus n tau 2, 1. Tau 2, 1 is positive. Okay. So this expansion tells you, this is an expansion basically in eigenstate. So if you were to insert a set of eigenstate of time translation, you would you would get something like this. So this quantity, this formula here is telling you that basically eigenstate of energy that are exchanged in this two-point function are only states with energy delta plus n with n integer. And what are they? Well, they are just all the descendants that belong to the representation of phi. Okay, so this is a sum over n is basically sum over descendant. These are the energies of the descendant in this cylinder interpretation. These are the energy of the Hamiltonian, which is the generator of translation along the tau direction. And these are the energies. And interestingly enough, we will see that you can even compute this Cn using radial quantization, and you should find that the Cn are positive because they correspond to phi cylinder En modulus square in an appropriate configuration that I'm going to discuss now. Okay. Of course, generically, this depends on n dot n bar, right? So they're not always positive. They depend on the scalar product, but there is a specific configuration in which this is true, and in that configuration, this Cn should be positive, and hopefully we will see that, or you can check yourself. Okay. So. Questions about this cylinder interpretation? So I would like to go on and define and to use this cylinder interpretation to tell you what is complex conjugation in our conformal field theory. Because this will will be useful later to define. So the goal of what I'm going to do now is to define, basically, given a state psi, I want to define the conjugate state. As you will see, this is not that trivial. Yes?
Sorry, a bit late, but in the second line, how did you get R1 in the numerator and R2 in the denominator related here? To my eyes, the same, just above.
Here?
Yeah, yeah.
I'm putting evidence, simplifying stuff. You can divide by, let's say, R1 square, and then one of the two divide by R2 square, okay? And then this remains, this cancels with one of the R2s, and it goes to the denominator. And then whatever is left, only a function of ratios and a scalar product. Good. Okay, so the idea is to define conjugate state. And to do that, let me make a step back to quantum field theory, generic quantum field theory. And how do we define conjugate state in Euclidean quantum field theory? Okay. So conjugation in Euclidean QFT. Because in Lorentzian QFT, so when you have Lorentzian signature, if you have an operator O at some time and X space here, you can write this object as e to the evolved operator at the origin. So this is just to the IHT. Let me put back the I so that all the generators here will be Hermitian. Minus I x vector p vector. And then O of 0, 0. And then the other into the minus I AHT plus I XP. Okay. I'm doing this because usually we don't think in these terms, so it's good to see it once. And then when you do complex conjugation, okay, you can ask what is the complex conjugate? The complex conjugate of this operator, dagger. Well, because of the fact that all the generators are Hermitian, and because of the fact you have i's in front, then when you do complex conjugation, take a minus sign, but also you have to reverse the order of operators. This is basically, again, if this object is Hermitian, so if O of 0, 0 dagger is equal to O 0, 0. Let me stick to this particular case. Then this is just O dagger. Well, this is just O of T and X. Okay, so this is a triviality, but it tells you that if you start with an operator which is Hermitian at 0, at generic point, the operator is still Hermitian. Fine, this is not a surprise. But then, let's see what happens. This is in Lorentzian, okay? Lorentzian. Let's see what happens when you switch to Euclidean CFT. When you switch to Euclidean CFT, what we are doing, we are performing a weak rotation. So we send time to minus I time or plus I time. So let's see. What are my conventions? So to pass, to go to Euclidean, we define t to be minus I t Euclidean. Okay. And then if you look at these formulas there, you see that O of Euclidean of t Euclidean x is given by the original operator. This for scalars. I'll do spinning operator in a second. Minus I t Euclidean x, which you can write as e to the plus h t Euclidean minus I x p O of 0, 0 times the other one. Sorry, it doesn't really fit. E to the minus h t Euclidean plus the s. And now when you take the converse conjugation, okay, you see that now you have to revert the order, but there is nothing that compensates this inversion of order, because now time t Euclidean here is real, there is no i's in front, and so this object here, surprisingly enough, becomes equal to the Euclidean operator inserted at minus t Euclidean. Okay, so in Euclidean QFT, performing a conjugation is equivalent to do a time reflection. Perhaps it's a bit unfamiliar, but that's what happens. Okay, and another observation that I would like to make is if you have spinning operators, then also weird things are going on with indices, because you have somehow to change, you have to multiply by some factor of I the time components of the fields in order to preserve, in order to make a scalar product SOD invariant. Okay, so for instance, suppose you have an operator O mu1 mu L in Lorentzian. Okay, when you go to Euclidean, you have to multiply each time component I'm not going to write it. Multiply time component by a factor of minus I. This is in order to enforce SOD symmetry. Right? Otherwise, you would have SOD minus 1, comma 1 symmetry. And so, because of this minus E, this minus I, when you perform, when you take the complex conjugation of such a field, okay, you still have to reflect the field in time. So you still get O Euclidean at time minus t Euclidean x. But now you also have to take into account that there are these minus I that gets conjugated, so you get an additional factor of -1 for special components. And so this results into a multiplication of each index by a matrix, which we call capital theta, mu1, nu1, capital theta, mu L, nu L. And capital theta, mu nu, is just delta mu nu minus 2 delta 0 nu delta mu 0. Okay, so this does not affect the non-time component, but it changes sign to the time component. This is a compact way of saying this. And so this is important because it's telling you that depending on which component you take to be the one that gets weak rotated, the conjugation will be different. Okay, so if you, let's say, for instance, okay, this is something to be aware of. For instance, let's say you start in Lorentzian where you have your Hamiltonian. So this is an example, okay? It's not really relevant for what I need, but just an example. Suppose you start in Lorentzian. You have the Hamiltonian, which is defined through the energy momentum tensor with an integral dd minus 1 x of t0, 0. Okay, instead Pj, the momentum is defined through the same integral, but of the component T0J. And then, depending on which direction you take to weak rotate, you might have different effects. For instance, if you take you weak rotate 0, x0, then you end up with an Hamiltonian which is Hermitian, while the momentum is anti-Hermitian. But if instead you decide to weak rotate some other component, let's say x1, then you would end up with p1 to be Hermitian and the Hamiltonian to be anti-Hermitian, for instance. Okay, so the conjugation property of fields depend on the quantization that you are using. This is very important. And so let me conclude by going back now to the case of interest. On the cylinder, we are using a quantization on the cylinder where our evolution operator is the time, is the vertical direction of the cylinder. So we can define a conjugation with respect to using with respect to that quantization. And so on the cylinder, okay, we get that operators inserted at time tau and vector n. When you take the complex conjugation, become operator inserted at minus tau and same n. Okay. And if we now translate this statement in the region in radial quantization, where tau is log of R, we see that operators in this quantization, operators inserted at R and vector n, when you take the complex conjugation, they go to operators inserted at the inverted point, 1 over R n. So this is the role of complex conjugation in our radial quantization is played by the inversion. Okay? And you can simply visualize this with a picture. Right? So this is tau equals 0, which is equivalent to R equal 1. And when a conjugation dagger sends you from tau to minus tau, and in the radial quantization, if you have an operator, so this is R equal 1, if you have an operator inserted at x mu, when you do the conjugation, this is equivalent to do an inversion. So this is sent at the point x mu over x squared. Okay, and to conclude, let me see how operators transform. How generators transform under this particular conjugation operation. And you can check yourself using either the definition of so a generator of the conformal algebra can always be written as a particular combination of say a generator Q, a charge Q of the conformal algebra can be written as the integral, indeed is minus 1x of some current. To be more precise, you want to write this as ds mu j mu, where this is some surface. Okay, so if you have a charge, you can write this as a surface integral of a corresponding current. In quantum field theory, you can take as a surface like a slice, and this will become the vector orthogonal to the slice in the time direction, and here you get J0. But generically you get this. And so you can use this definition and see how different currents, because they're tensor, how they transform under inversion. Some of them pick minus sign, some of them do not pick minus sign. And the bottom line is that dilatation under inversion, they stay the same. That's nice. If you have spin, you perform a conjugation. You can imagine that when you invert, you're basically looking at spinning on the other direction. So you take a minus sign. But the more important one is P mu, dagger. If you remember what we said yesterday, composing a translation with the inversion corresponds to perform a special conformal transformation. K mu. So in radial quantization, the operator P mu is not Hermitian at all. It's not even anti-Hermitian, but is related to the special conformal transformation by this relation. And this will play a major role when we discuss unitarity constraints. Okay. Are there questions?
Yeah, it's just the index. Should it be down correct like minus?
You mean where? Sorry.
Very last index.
Yeah, of course. Thank you. Sorry. Other questions? Yes.
If we consider the two-dimensional case,
Yes.
can we still obtain the remaining generator in the same manner?
Right. In the you can.
The conjugation of the
Right. You can obtain the transformation properties of all generator in the radial quantization by just doing this. You can if you want you're talking about the Virasoro generator, or yes, you can write them as an integral of the energy momentum tensor divided by some residue of the energy momentum tensor. So if you perform an inversion, you can check how things transform and you can obtain the conjugation properties. It also works in that case. It's even simpler because in that case, you basically, so in that case the slices here are S1, so it's just a circumference, so it's literally flat. But yeah, it works also in that case. Other questions? Okay, let's stop here.